There we go. We're good. Okay. So in the previous lecture, I had talked about, kind of the theory behind radiation. And now we're going to start looking at some of the processes for gamma and X-ray, performing gamma ray and X-ray inspection of parts. So this first part is for when we have a gamma ray, when we're doing gamma ray inspection, we have to have an isotope delivery system. Somehow, remember those isotopes are radioactive. They're going to be giving off radiation. There's no way to shut them off per se. And so we have to be able to store them safely so that we're not exposing ourselves and others in the environment to the radiation when we don't want to. But then we also have to be able to open up our, provide that exposure when it's needed. And so this is kind of a schematic of an isotope delivery system. What you have in the middle, this is in the stored position. So this is when we're not using it to actually image something. But what you have at the very center there is the source, kind of showing it's giving off radiation. And it's inside of a, typically like a lead-lined box. And that's the shielding. And so that's going to, when we're not using the isotope, that's going to contain that radiation. On the left, we have what's called the crank out or the crank, which allows us to put this in and out of the box without touching it. To the right is going to be our exposure window that we're going to put near what we're testing. And so what happens is there's a flexible cable going from that crank to, at the end where there's a source, there's a little kind of container that holds a non-shielded container that holds our gamma ray source. And so if we crank this cable out, that source is going to slide out through a tube. And ultimately, we're going to crank it out until it gets into the end there that's called the commutator. Or sorry, collimator. I don't want misspeaking. But the collimator is going to be, it's still going to have some shielding, but it's going to essentially have a window on one side of it, or one area, where it's going to allow that gamma radiation to escape in a known direction. And so we would put then whatever our object is, you can see here where the radiation is essentially going down, we would place our object below the collimator in this case, and then the film would go behind that, or the detector would go behind that. And so in this tip, what we have here is this the black piece coming in from the right is the end of that flexible cable. So that flexible cable is being cranked in and out using the drive over here, the drive cable. And it's going to have the little holder on the end, and then you can see it's a fairly small piece of radioactive isotope. And when it's inside this holder, the holder, though it's made of metal, it's not going to block all of the radiation that's coming out. And so we can slide that part, or we can slide that radioactive part, material in, out and back into, so then we can bring it back in when we're done using it to store it. Okay. And so I have a video here that kind of shows this process in action. So if we look at kind of a cutaway of what was happening, or what's happening in this process, here's a cutaway schematic of an engine, a turbine engine. And we have our source down here, our gamma ray. Here they call it a projector. In the video, he called it a camera. The control crank. So here, when you turn the crank, it's going to bring the gamma source through the guide tube. And in this case, the guide tube's been inserted down the center shaft of the engine. Right? And you remember looking at like the JT9 when we took the spinner off? Remember, you could see all the way down to the far end of the turbine inside the JT9 when you look through that, through that central shaft, that spool shaft. So then the source here gets brought in this area. Here's your combustion chamber right here. So this is a combustion chamber inspection. So here's the compressor area here. The turbines are back here. Our iridium source is between the combustion chamber. The film for the imaging has been placed, here, and this is to image the combustion chamber, whether it's the liners or the source. So here's an example kind of that setup, right, going down through that center of that engine. That looks a lot like a JT9 in the picture. I'm not quite sure what it is, but. And so what you get is an image that looks something like this. And now you've all seen, you've inspected combustion chambers, right? We did it earlier in the semester with remote visual inspection. And you can see how this looks a lot like, a combustion liner right here. So this is the resulting image you get from this process if you're doing it on on an engine. This can be applied in multiple different areas. It can be applied, we used it for engine inspection like this. We've used it for wing spar inspection, landing gear trunnion inspection, a few of the other, big, heavy structural areas that aren't necessarily easily accessible were kind of a common area that this was used. Again, a lot of things are actually moving away from this, however, just because there are other techniques now that are out there that are maybe safer or less expensive to deal with. The other type of radiography that's often performed in aviation is X-ray. And so X-ray is, rather than having a source, a material that is constantly giving off some kind of a radiation, gamma radiation, we're going to produce X-rays using an electrical X-ray tube. So an X-ray tube is it's a type of vacuum tube. We apply a very high voltage to it. You can see here, this one is talking about 30 to 100 kilovolts, or 30,000 to 100,000 volts. And that is going to cause the release of electrons that when they strike an anode structure, a target on an anode structure, they're going to release X-ray. Okay. So we have our high voltage power supply. You've got the cathode here on the left that's going to be releasing the electrons, the anode on the right that's attracting electrons, and when they hit this target material, that's going to have the X-ray beam. And there is a collimator on here where the X-rays are directed in a certain direction. So here's kind of a video of one of these operating and kind of this gentleman explaining the theory. So those are two primary radiation sources used in aviation. In some cases, you will see additional, we have gamma ray and X-ray. There is some work as well being done with neutron radiography, which is another technique, but not as common in aviation yet, although you're seeing more and more kind of in industry, I guess. But then we've released, so we have these sources of radiation. That radiation is then allowed to pass through the object that we're looking at, or we want to examine or inspect. And then we have to detect how much radiation makes it through different areas and create an image or something that we can see. Or it doesn't even have to be an image. It can be, in some cases there's computer interpretation where it's just kind of like thermography. If you're hitting a radiation detection panel, it's going to measure the intensity at each pixel or each point on that panel. And then if there are algorithmic and machine learning based systems now that can, kind of compare what's the energy at this pixel to the pixel next to it to the pixel next to that and perform analysis without non-visible analysis. But your oldest, originally, we had films, and they started out, they're a silver salt. So did anyone play with silver salt in chemistry class in like high school or anything? You've heard of it? Okay. So silver salt, when it's silver salts, silver chloride and other items like that, when they are exposed to radiation. That radiation can be light, which is what black and white films are based off of, like, or radiation in this case. It turns from its white color to a black color. And depending on the intensity of the radiation, it can be somewhere on that spectrum. So, a little bit of radiation is going to turn it a light gray. A little bit more radiation is going to turn it a darker gray. A lot of radiation ultimately will turn it to black. And so that's how our image is being developed. So the first kind of films that were out there were one-dimensional. They were almost like a strip. But what's most common, what was seen for very quickly after that, and what was seen for years and years and years, was a two-dimensional film that creates a picture or an X-ray that looks like a photograph that we're familiar with. Today, we use real-time X-ray and radiography detection equipment. And so real-time these are these digital detectors. They are semiconductors that are affected by these radiations, X-ray and gamma radiation, that changes their conduction. It's the same way like a light sensor works with visible light, or the sensor in your camera, reacts with visible light to create a two-dimensional picture using a camera. So it's similar technology to what's in your cell phone or what's in other things or a digital camera, but tuned to react to a different wavelength of energy or a different type of energy. And so this will reconstruct a digital image in a computer, one that we can see, or as I was alluding to, one that can be pixel by pixel analysis performed on it in order to do more than just a visible or a visual inspection, but actually can perform more of a quantitative type analysis on it. And then kind of the most complex version of this is computed tomography, or what most people have heard of called a CT or a CAT scan. And in CT is we still are taking essentially a 2D, we still have our two-dimensional array. We still have a single, a source of energy, typically X-ray energy in this case. We're not going to use gamma ray with a CT. But you have an X-ray source, and you have a digital collector. But instead of just taking a single image, it's going to take many images, one after another, in very quick succession. Ideally, they're as quickly or as instantaneously as possible, but if your object isn't moving, or is moving in a predefined path where you know what's happening, say you're turning that object, you're able to then take all those images, those 2D images, and essentially overlay them one over another, over another, over another, stack them up, and you're able to produce a three-dimensional image. So a CT, at the end of the day, is essentially just a three-dimensional X-ray. Okay. I'm assuming a lot of you probably have had a CT at some point, right? You had to lay very still or stand, you had to stay very still when you were doing it. That's because it was taking all these images and you want them to line up. You don't want them to get blurring between your different images. Okay, that's why that's the case. So what do these look like? Here's what a one-dimensional X-ray looks like. And so what happens here is it's essentially a strip where the X-ray is allowed to penetrate from one edge, and you can see the areas where more radiation hits the edge, you get a deeper kind of penetration of the radiation. So it gives you intensity over a distance, but it only gives you intensity over a linear distance. And what they've done here is you can see between 6.5 and 7, there's a lot of little spikes. So this is just they've blown up this area between 6.5 and 7. And these silver crystalline salts, they're very, very fine particles. So you can get very high resolution And so where you can actually blow them up by using an enlarger, things that were used for photography back in the past when film photography was the standard. If you make a 2D version, you've probably seen most common X-rays that are two-dimensional. What's this right here? Any ideas? The composite panel, right? It's a composite panel. This is just a standard layup in this area. And you're able to see some of the fiber orientation. And then that panel, where it's just a couple layers of fiberglass, it transitions into an area that has a hexagonal core material, right? And you can see that we have areas of differing, different amounts of resin in different areas are going to block or allow the transmission of more or less signal. Now, I believe on this one that this is an inverted image. I don't know what this was off of particularly, but remember with typical X-rays, the areas where X-rays are able to penetrate easier tend to be, those are the darker areas. And the areas where X-rays are blocked more are the less dark areas, right? They're the areas that remain whiter. I believe this one is inverted in that the areas, this area right here is going to have a lot of resin kind of filling those gaps. That would probably block more X-ray, than the thinner materials here or here where a lot of these honeycombs, the face materials are bonded on the top and the bottom, but the honeycombs themselves should not be filled with resin. That would kind of defeat the purpose, right? So I believe this image has been inverted. And sometimes that's done in order to help see certain attributes or certain aspects or details that maybe are more visible this way. It's just like when we did thermography where you're able to change the different color overlays, right? You can do the more iron colored, you can do the rainbow colored, you can do the white hot, or you can do the white cold, right? This is the same kind of a thing. We can change kind of the overlays based on the intensity of the radiation that's involved. Real-time two-dimensional X-rays in aviation are commonly used here. What's this from? What's that? TSA, security. This is your X-rays as you go to board a plane. Right, so now we go to 2D. So this is X-ray, and we use a digital detector rather than film, right? It would be, you think TSA is bad now, it'd be really a slow process if they had to develop, every single picture, because the silver salt X-ray film has to be developed just like visible light film had to be developed. It has to be, there's different chemicals you got to put it in, it's got to be fixed, and then ultimately it's got to be printed, you got to enlarge it. And so, two-dimensional real-time X-ray, where now there's color coding based on it. They can actually, depending on intensity, the X-rays you see can it's not a true 3D, although some of them nowadays are almost going into that CT CAT scan category where it becomes more 3D. So most of your new systems are 3D, but the older systems, even though they were 2D, depending on how intense, they would start with like a lower intensity X-ray and they would increase it, and it would change what's able to be imaged, and then that kind of creates this more detailed view. Okay. Any ideas what you're looking at here? Some of the objects in this individual's bag? The what? A radio? Where's the radio? Yep, right there, boombox. You can see it's got like an antenna on it. I never said this was a new picture. Anything else? What? A couple belts, or at least belt buckles, right? These are probably the belts wound up behind them. This down here, anyone know what this is down here? Zip ties. Plastic isn't going to show up as well. What's metal that looks like that? No, no, no. That's like a pocket umbrella. Yeah, that's like a travel umbrella. I'm trying to remember what else was in this image. I think there's a shoe right here, if I remember right. There's kind of a shoe back there behind the boombox. And the other one right there. So, you know, the technology's gotten better in digital. There really isn't a lot of use for the older film-based, although I have seen film-based done before. We did have film-based done on some of the aircraft. And I say we've seen it done before. We're talking back in like 2009 is the last time I saw it being done. So, yeah, I'm guessing most of those companies have gone to two-dimensional detectors. I've priced this stuff out. The detectors aren't too bad cost-wise. The X-ray source was the big cost driver when I've priced it out. So the detectors, if you're not going super high resolution, actually are not in the industrial use scale of things are not too bad. You know, they're a car, they're a nice car, but you know, a $50,000 car or a $50,000 detector, if it means you don't have to tear an engine apart to do an overhaul, you just saved yourself $950,000, right? So in the great scheme of things, they're not too bad. So CT, computed tomography, looks something like this. So this is a version where you can see this X-ray tube. It's going to create a strip on the detector array, and then as this detector array, or as it's taking pictures, the test piece is going to be moved vertically up and down. That's going to create those slices that can be laid over top of one another. Other versions allow the part to be rotated. We can rotate them and move things up and down. So the detector, so here, you know, the part can be moved up and down. Here, the part is rotated, and then the actual detector and source can be moved up and down. Okay. So producing 3D images. Now the video I've got here is 12 minutes, so I don't necessarily show it in class unless I got time. So I'll finish out the slides and then I can kind of come back to it. But ultimately, here's your kind of, you know, a single slice of a CT, and you can see this is a turbine blade. What kind of features are you able to see in this turbine blade? And what would that allow you to see if you were inspecting it? What do you see on this turbine blade? What's that? What are all these circles? Where are these little slots on this side? This is the leading edge, this is the trailing edge here. The cooling holes are known as gill holes, right? So air is able to come from the hub and travel through these main passages right here. And, you know, sorry, through these passages, these are hollow blades, and out through those cooling holes, okay? So you would be able to see, like, if you had cracks going between the different holes or chunks, or internally if you had some kind of cracks forming inside the blade. If we look at it from a 3D perspective, we get something that looks like this. So we take all those slices, we set them on top of one another, and then we can always look in. You see here, it's even cut away, right? It's created it, but then you can like zoom through it and travel through it, right? It's a digital image. So we're able to go inside the blade to look at what's going on. You can see those are pretty complex geometry inside of them. More than just a hole with some other holes drilled in it. Okay. So this is commonly used more in that kind of an overhaul, that component overhaul level, where they'd use an industrial X-ray, a standalone. This would be, rather than, you know, the X-ray source, the portable source and the detector, this is like a cabinet. You set the blade in, and it's going to do the inspection for it. Okay. So that wraps up the slide.